be quite energy efficient, and because if you use electric field without current, then you can avoid a great deal of this Joule heating in the devices. So this is the basic background. Of course, Prof. Thomas already showed that's the main background for example, for the data storage. Now, actually, most of the data, so they actually are stored in a digital form, mostly in the hard disk, and also the data centers consisting of the arrays of hard disks. And now all our data is actually managed, for example, in this kind of hard disk. But now, if you look at our hard disk, HDD, this mechanical hard disk, so the right head, we use this coil with the current. Of course, during the information writing, you pass the current, and then it generates lots of Joule heating in the coil. Of course, reading, we use this GMR sensor. But now also the recent commercialized these MRAM structures. We also use this current to try to, which generates the magnetic field, and then try to reorient the magnetization of the free layer. But if we look at the energy consumption of this kind of devices, for example, MRAM, the current energy consumption is around 100 picojoule per bit for energy storage. And the STT MRAM is much more energy efficient. It reaches 1 picojoule per bit. It's like 2 orders of magnitude lower. Actually, according to the International Data Corporation, in 2024, that means around 5 years up to now, from now, and the total electricity consumption for data storage will be like more than 5% of the electricity of the entire society. That's actually quite a lot. Actually, there are also alternative approaches which we could avoid this current. For example, we can use electric field. So what's the difference between electric field and the current? If you apply a voltage to a conductor, that generates a current. But if you apply a voltage to this insulating ferroelectric oxide or piezoelectric oxides, that only generates negligible current on the order of nanoampere or even smaller. So in this case, the voltage generates a string or piezoelectric string if that's the polarization switch inside the ferroelectric material is non-180-degree switch, that's so-called the ferroelectric switching. So we can use this string to modulate the magnetization or magnetic state of these thin films. If we could like epitaxial groom, or for example, if we could epitaxially groom these magnetic thin films onto these ferroelectric oxides, because we want the most ideal case is that we could realize epitaxial growth of these ferromagnetic thin films onto ferroelectric oxide. Because if we use this electric field to try to produce the piezoelectric string from these ferroelectric materials, it actually produces biaxial compressive string. If we have this single crystalline or epitaxial this ferromagnetic or antiferromagnetic thin films, we try to squeeze the crystal from a certain direction. That actually gives you the most efficient modulation. However, if we want to grow this like intermetallic alloys or some like especially these metal films onto ferroelectric oxides, there are several challenges. If you want epitaxial growth, you need a high temperature to provide enough thermal energy to let the atoms move to the equilibrium size. But somehow, most of these magnetic alloys, they are actually very active. So chemically, they are very active. At high temperature, they could easily form second alloy with these oxide substrates. The other thing is a weighting issue. The metal and oxides, they have completely different surface energies. For example, if you have a drop of water onto a piece of glass, actually it has a so-called weighting angle. This is completely the same thing for the high temperature growth of metal or oxides. The other thing is the lattice mismatch. For most of intermetallic alloys, their lattice is around 3 angstrom. But for these perovskite oxides, it's around 4 angstrom. This large lattice mismatch could easily prevent the epitaxial growth. But somehow we could find some like a suitable substrate which with this high temperature thermal stability. For example, this is a manganese platinum, is a conventional antiferromagnetic intermetallic alloys. We could like successfully grow on this magnesium aluminum oxide, this bilayer oxide substrate. We could realize this epitaxial growth with relatively smooth surface by optimizing the growth this battery power and also the air argon pressure. Also, this is this TM of the magnetic platinum thin films, epitaxial groma MO. Actually, it shows a relatively good interface. So actually, with this kind of technique, we could grow actually this magnetic alloys or oxides. The other thing, for example, I put this like for this iridium. This is another example. Iridium is a conventional magnetic intermetallic alloy with a first-order magnetic phase transition. At low temperature, below like 350 K, it's a antiferromagnet. But like above this one, it has a first-order phase transition, so its lattice will expand by around like 1%, and then it undergoes the transition into this ferromagnetic state. During this transition, its resistivity also abruptly changes. So this material system actually is a system with electrical magnetic structural properties closely correlated with each other. So if we look at this material system, actually it's quite ideal for us to like realize so-called multiferric heterostructures. If we can integrate epitaxial group this iridium onto this ferroelectric oxide substrates, the piezoelectric string can modify the structural properties, and then its electrical and magnetic properties will be changed simultaneously. For example, this is a growth we performed. Like, for example, this is a barium titanium oxide. It's a relatively high temperature. It's very high temperature stability compared with like PMNPT. We can perform growth maybe at 500 Celsius degree or 600, and then do post annealing at 700 or 800. We could get this like a single crystal epitaxial thin films, 001, 002 peak. We have this is like because of large lattice mismatch. Iridium, the lattice constant is around 3 astrom. Barium titanium oxide is around 4 astrom. It is a cubic or cubic. It's very difficult, but in plane 45 degree rotation will make it very easy. So this is actually the 45 degree rotation in plane epitaxy. And this is a TM image of the iridium on barium titanium oxide. Probably it's black, the contrast is not good, but actually the interface is very good. In this kind of multiferric heterostructures, if we now if we look at this transport curve first, the iridium has a first order magnetic phase transition. Initially, if we don't apply any electric field to the barium titanium oxide, there's no string, no piezoelectric string, and then the magnetic phase transition temperature is around this 350 K. But if you apply a piezoelectric string, this transition is shifted by 24 K to 376 K. And then around this phase transition point, previously here is already the ferromagnetic state. And then after applying the string, piezoelectric string, actually it becomes the antiferromagnetic state. Then around this phase transition point, use the electric field or the electric field produced piezoelectric string, you can completely reverse the magnetic order in these materials. As a result, the resistance of this intermetallic alloy changed quite a lot. For example, here it's 100 Celsius degree. The resistance changed by like 22%. Consider that this material system has a very large carrier density of 6 times 10 to 22 centimeter cubic. It's a very metallic alloy. So this large resistance, 20% resistance change at around 100 Celsius degree is quite large. This is, of course, because of the magnetic phase transition. This is actually quite similar to the so-called phase changer memory, and also the actually, to me, it's like the CMR system, and also the new concept proposed by Thomas today, so-called this LIU texture magnetic systems, all are similar to this kind of stuff. If you now look at this kind of heterostructure, iridium, initially without any electric field, so it's at 100 Celsius degree, it's full of ferromagnetic domains. After you apply electric field and piezoelectric string, it becomes completely like antiferromagnetic. So now we actually, let's just simply try to estimate what's the energy consumption for this kind of multiferric heterostructures. Now, if we remember that the MRAM is around 100 picojoule per bit, and the STT MRAM is like the 1 picojoule per bit. The polarization switch energy for just 1 bit, consider we can make this device very small, like 100 nanometer by 100 nanometer by 100 nanometer. This is just a small cell. The energy consumption for this bit just simply from this polarization switch point of view. Of course, we may have some like other mechanical energy loss, but like some other. But only from this point, the energy consumption is like 10 to minus 17 joule per bit. This is like 5 orders magnitude lower than ST-RAM, MRAM, and 7 orders magnitude lower than MRAM. So from this point of view, the so-called multiferric heterostructures, they have the advantages of super low energy consumption. So now we talk some like antiferromagnetic spintronics, of course. Again, all the advantages of antiferromagnetics, because of the zero stray field, it's insensitive to external magnetic field. And because of that, we could also realize higher packet density for memory devices. Because now for the current, this HDD RAM, this nano texture, this nano particle films, they still have this non-magnetic, between the magnetic particles, they have this so-called non-magnetic space layer. But if we are using these antiferromagnetic materials, we could like make this data bits close to each other. So that in that case, in that way, we could like further enhance the packet density. The other thing is that due to this catting, the catting freedom of the AFM spins, antiferromagnetic spins, the intrinsic spin dynamics is very fast because that involves the so-called spin flop, this antiferromagnetic exchange at the field. Typically, it's like this zero field AFM resonance frequency is the gamma H spin flop field. For the spin flop field of the antiferromagnets, it could easily like reach several ton Tesla or even more than 100 Tesla. So finally, this frequency becomes like more than 10 Hertz. Actually, some like a very early theory, for example, is on this so-called antiferromagnetic spintronics. For example, like in 2006, Prof. McDonald's group, like he proposed, we can use spin torque to realize GMR in antiferromagnetic metals. At that time, like the concept of it's like still the concept of antiferromagnetic spintronics is not like coming yet. So that time, like this concept is a little bit conservative because in that case, people probably only may consider this kind of in metals. So that's why actually in this review paper by Prof. McDonald, like, he proposed so-called antiferromagnetic metal spintronics. Of course, now in 2011, this Thomas groups, this similar work, they actually reverse the order of this antiferromagnetic layer and the ferromagnetic layer in this just asymmetric this color structure, and they demonstrate that at low temperature, for example, 4K, it could like nicely work. And also this in like Chavi Marty's work. Actually, I had this overlap, a little bit overlap with Chavi in this Ramesh group, like in Berkeley. So actually, he used this iridium. He actually used this phase transition of this iridium, and also of cooling field, to try to manipulate the spin axis of the antiferromagnetic state of iridium after the cooling down. So in this case, he could also realize two different resistance states using the anisotropic magnetic resistance of iridium in its antiferromagnetic state. Actually, these are very early examples that you can use antiferromagnetic materials for spintronic device applications. But somehow, for example, this one is still based on the manipulation of these ferromagnetic layers, and this one is you need this thermal heating and also this cooling field. It's not really easy, convenient for application. But the real actual breakthrough came like in 2016. This Thomas group, again, they demonstrated electrically they can manipulate the spin axis of this antiferromagnetic semiconductor, copper manganese oxide. So this is actually a very nice push. Now, actually, we also talk about this somehow this so-called anomalous Hall effect in antiferromagnets. That's the device point of view. And then this one, we can talk about this like more like physics point of view. So this series on the anomalous Hall effect actually reveal like three kind of mechanism. First is like the intrinsic deflection that involves mainly Berry curvature, and the other is like the side jump that is more related to all even the spin orbital. Actually, that spin orbital related scattering from either the atoms that in the crystal or the defects, or the third one is like the school scattering. So with this kind of background, it's like the other breakthrough in this also breaks in the atmospheric effect for antiferromagnets. In 2000, this 14 McDowell's group again, and they predicted that in this magnesium-3 iridium, there is a notch, this barrier curvature induced by the non-collinear spin structure. And of course, this Claudius group, they also predicted the atmospheric effect in the same year, but this is in the magnesium-3 tin and the magnesium-3 germanium. Actually, there are some like difference in these two papers. For example, this one, all the theoretic calculations, they were done for cubic antiferromagnets, magnesium-3 platinum and magnesium-3 iridium. These cubic systems, they are actually, if you have very strict cubic symmetry, actually they are very hard antiferromagnets. It's very difficult to observe or realize the atmospheric effect in the single crystals because of the very strict cubic symmetry. Only if you can apply a uniaxial string to break the strict cubic symmetry, you could realize the atmospheric effect, possibly in magnesium-3 iridium or magnesium platinum. But somehow this material, this actual theoretical calculation is based on this magnesium-3 tin and magnesium germanium. They are hexagonal. Actually, that's so-called soft antiferromagnets with like a small anisotropy energy. So in this case, it's very easy now for experimentalists to realize. For example, then in 2015, this Nakajis group, they observed a very large atmospheric effect at room temperature in magnesium-3 tin. Of course, now if we look at the atmospheric effect, it's not really related to previous we thought like the atmospheric effect is kind of a feature for ferromagnetic materials, but now it's more like the transport properties. For example, now in some non-ferromagnetic systems, we have also atmospheric effect. For example, this non-collinear antiferromagnets, and also now actually more recently in this non-magnetic two-dimensional materials, actually the barrier curvature dipole induced by inversion symmetry breaking could also generate the so-called second-order non-linear atmospheric effect. It's a second-order one. It's mainly from this kind of two-dimensional materials. And also now, except for the barrier curvature mechanism, if you have a larger school scattering, you can also have the atmospheric effect. For example, in this non-magnetic magnesium zinc oxide or zinc oxide heterostructures. Actually, we also worked on another antiferromagnet, because magnesium platinum is single crystal, very difficult to observe the atmospheric effect. But somehow, it's very difficult to realize strict cubic symmetry in thin films. So we start to grow these magnesium platinum thin films, because this material, magnesium platinum, is quite similar to the iron rhodium. It has a first-order magnetic phase transition, but this phase transition is antiferromagnetic to antiferromagnetic phase transition. And then, so for this low temperature antiferromagnetic phase, it's non-collinear. And then from this theoretical calculation, it has very large barrier curvature. Then it could have the so-called atmospheric effect. But in the collinear phase, it's just a trivial for this barrier curvature. So we don't have any atmospheric effect. And then we grow this magnesium platinum thin films epitaxial on this barium titanium oxide at high temperatures, around like 700 Celsius, 600 Celsius degree, and annealed at 700 Celsius degree. So we found this, for example, this first order this transition is reflected in this transport curve. For example, this resistivity has an abrupt change around the phase transition point. It has a hysteresis, and also the lattice structure of these thin films with it also has a very abrupt change. They are saying like at low temperatures of this kind of thin films, we have very large atmospheric effect, but at high temperatures, we didn't see any like atmospheric effect. Now in this kind of multiferric heterostructure, again, we do the same thing with iron rhodium. We use the piezoelectric string, try to modulate the phase transition temperature of this, the first order phase transition of this magnesium platinum. So initially here, around here, this point is already the collinear phase. So there's no atmospheric effect. But if we apply an electric field to this stack, the piezoelectric string generated from this barium titanium oxide will be exerted to this thin film, and then its lattice is compressed, and the phase transition temperature is enhanced again by like 20 K, and then from here, and then becomes here. This now already becomes so-called non-collinear phase. So initially, we don't have the enormous Hall effect. After you apply an electric field, isothermally, we could turn this on, make this a non-collinear spin structure. And then this Prof. McDowell's group did calculations for us for this kind of strained thin films, because these thin films, and we found that in this kind of thin films, the enormous Hall conductivity is around 81, and we got this 74. It's actually get a very quite nice agreement. Also, after the publication of this work in Nature Electronics, Prof. This Christopher wrote a news. He said probably this is quite important because from the energy point of view for antiferromagnetic spintronics using electric field. Also, this work was like highlighted by the Nature Physics 1 month after the publication. Also, like Science also chose this as a research highlight. We can use the electric field to switch the spin structure of antiferromagnets. Now, in antiferromagnetic materials, although this non-collinear spin structure could be very interesting, but somehow if we look at all the material systems, non-collinear systems could still be rare. Most of the systems are still collinear. So we now think, can we use piezoelectric string to modulate, to universally modulate the spin lithotropy, the magnetic lithotropy of antiferromagnets, like magnetic platinum. For now, we will continue work on this magnetism 50 phase. These are collinear antiferromagnet. The low temperature growth on PMPT give us like a textured film with like at least two kind of orientations. At room temperature, there's no measurable magnetization with this XMCD and also this VSM or squid. But if we grow a soft cobalt iron layer on top of magnetic platinum, we have very large exchange bias, and this kind of exchange bias is very robust, even like after 500 cycle measurements. So for this kind of antiferromagnetic thin film, magnetic platinum actually has a very high near temperature, around 975 K. So that indicates the antiferromagnetic exchange coupling energy of this material is very high. So when we apply a magnetic field of like a 9 Tesla to this material, thin films, we get just a negligible magnetic resistance, around 0.01%. But if we apply this piezoelectric string or electric field to this film, we found that the resistance at room temperature could change by like 2%. It's like 2 orders of magnitude higher than this magnetic resistance. So if we look at our this resistance curve versus the electric field, we found actually it's quite similar to the piezoelectric strain curve of the PMPT itself. For example, this red curve is a strain curve versus electric field for the PMPT. And also this is another strain curve. Also this mimics the strain curve of the PMPT substrate. And then we also consider our resistance curve is similar to a strain curve, but like how about the other mechanism, like so-called electrostatic doping. So if you have the electrostatic doping, the Thomson Fermi screen length for this material film is very short. It's only like around 2 angstrom. But our film thickness is around like 40 nanometers. So it's quite far away from the total thickness of our thin film. Or we also measured the carrier density of our thin film at the high and the low resistance state and the high resistance state. And it turns out there's almost no measurable change. But now we found actually for this high and low resistance state of this thin film, the exchange bias, if we grow this cobalt iron on this top of this magnetic platinum, the exchange bias between this double layer system actually has a significant change. For example, this is the blue curve and the red curve. They are actually the low and the high resistance states respectively, so they have a very large change. But we also find this soft ferromagnetic layer is not sensitive to the strain at all. So we have the exchange bias change, but the soft ferromagnetic layer is not changing. So we infer that there are definitely something changed in the antiferromagnetic layer. And then we propose a possible mechanism that in our textured film, we could have like at least 2 different spin orientations. Under this biaxial piezoelectric string, the spins, some in the one texture will be rotated from in plane to out plane and then give you the lithotropy magnetic resistance. This kind of memory device, we can also write with so-called unipolar switch for ferroelectric material or for ferroelectric substrate. And this kind of information writing is very stable. even under the magnetic field of 14 Tesla, because there's no current. So you will not have the effect from the Lorentz force. The other thing, like the low resistance state induced by the piezoelectric string, it's very stable. For example, we tested this state in our lab like for 10 days, more than 10 days. And the resistance fluctuation is around like 0.05%. It's like 2 orders of magnitude lower than the resistance modulation. That's 2% in our case. The other actually interesting point of this material is because of it has a very high near temperature. So at room temperature, the manganese platinum itself, the resistance is very, very stable. There are two reasons. One is because of this high near temperature. For example, we tested this material up to 60 Tesla. The resistance change of this thin film, of this low resistance state, this piezoelectric string induced low resistance state, only fluctuates around 0.1%. That's because actually this material has very high near temperature, and then the antiferromagnetic exchange couple field is very high, and then the spin flop field is very high. So it's more than 100 Tesla. So this 60 Tesla is not like doesn't affect the spin this configuration. The other thing is like manganese platinum, all these manganese-based intermetallic alloys. There are some kind of like dirty transport systems. They have like very large scatterings, and then in case this orbital scattering is suppressed for the strong magnetic field. But if we compare this manganese-3 platinum with manganese platinum, manganese-3 platinum, it has a relatively low near temperature, around 475 K. Under 60 Tesla, the magnetic resistance reaches around like 2%. That's almost the same order of magnitude with our electro resistance. So that tells us we need a high near temperature magnetic antiferromagnetic alloy to realize a strong, very strong magnetic field in sensitivity. And then we think if we are really use piezoelectric string to modulate the spins of the manganese platinum, can we further amplify this via Taylor-Junction behavior? And then we put a very thin this ML layer, magnesium aluminum oxide, around 2 nanometer. And this is I put this asymmetrical platinum. We tested this two-terminal resistance as a function of this piezoelectric string. We found a similar curve, but like this time at room temperature, it changed around 11.2%. This is actually a very large value for this antiferromagnetic piezoelectric this Taylor-Junction. Because like for the previous antiferromagnetic Taylor-Junctions, typically at room temperature, this ratio, this change ratio is very small. So this work again, this year was selected as a research highlight by Science, and then said, okay, now we can use a string to control the antiferromagnetism, and that's an operation in sensitive to magnetic fields up to 6 Tesla. Of course, if we think about all this kind of stuff, this idea is not really new. Use a string to control antiferromagnetism. For example, this is a theoretical simulation from this UC Riverside group, this Kaman and Lake. They actually simulated all the manganese-based antiferromagnetic intermediate alloys. The response of antiferromagnetic spins upon this string. So this actually, the results actually agrees with our experimental result. The other thing is like this is actually the previous studies on this string control antiferromagnetic properties. For example, this BFO. If you apply a string, this work was early in 2015 from a Beijing group, Prof. Jiang Yun's group in Beijing. They proposed that they also see the change of the exchange bias. They proposed that the spin axis of BFO actually is modulated by this string from PMPT. The other thing, this is from like Greg Kamen UCLA's group. They proposed, they studied this nickel oxide bilayer exchange bias system. They concluded that in some piezoelectric string region, actually, it's not really the rotation of the ferromagnetic spins, but somehow, and the most important thing is actually the antiferromagnetic spins that rotate. Also, this is another work from this Tsinghua University from Prof. Lai Cengwen's group, and they also studied this nickel oxide, this bilayer system. They found that they use piezoelectric string, they can actually change the spin axis. They actually studied this by this linear dichroism. This is actually from this Mainz group, from here, Philip Chloe and Mainz group. They use this mechanical string for this manganese gold. They found also the linear dichroism signal changes upon this string. And this is a recent work from this Prof. Sun Cheng's group. They also found this manganese gold the spin axis is changed upon this piezoelectric string. So if we now think about all this kind of stuff, it's not really unique, this kind of switch for a certain material. It may be universal for all the antiferromagnets. If now we look at the energy term for this string one, the magnetoelastic energy induced by a piezoelectric string is just simply could be expressed like this one, lambda s sigma. Lambda s is the magnetostriction, and sigma is the strain. So the origin of this lambda s is just a long-range magnetic order and the spin optical coupling. It's quite similar to the anisotropic magnetic resistance of antiferromagnets. So from this kind of point of view, so we can finally say, although antiferromagnets cannot sense magnetic fields, they can feel strain well like ferromagnets. And finally, we tentatively propose this idea to emphasize that we can use string to modulate the anisotropy of antiferromagnetic materials. And then we call this antiferromagnetic Piezospintronics. And finally, I would comment on and a common remark on the so-called epitaxial string versus piezoelectric string. There are two kinds of string in our thin films. For example, you have so-called epitaxial string that comes from the lattice mismatch between the substrate and the thin films. That's static and irreversible. That quickly relaxes from the interfaces. And typically that range is around, it's very short. It's just interface region. It's around 1 to 30 nanometer, depending on the lattice mismatch. But for the piezoelectric string, it's dynamic and reversible, depending on the electric field you applied. And the string mediation is almost 100%. The string mediation is almost 100%. And the other thing is long range. It can up to like micrometer. For example, this work, the experimentally like this drama group, they found like if you grew even like 100 interfaces, this so-called consisting of 100 superlattice interfaces, the surface of the superlattice has completely the same string with the interface when you apply electric field to the piezoelectric substrate. So finally, I would like to thank you for all your attention. Thank you.